Today I will discuss dimension of a vector space or dimension of a subspace. So before we have to know what is dimension, we first have to know what is basis of a vector space. Let this be a field of scalars denoted by capital F, and this be a vector space denoted by capital V. This vector space has three components for its elements. Means the elements are like X, Y, Z. Then what will be basis? Basis is nothing but a set of vectors. Basis is nothing but a set of vectors with this type of elements X, Y, Z, or I mean to say the number of components of the elements of this basis set denoted by capital S is same as that of the vector space. If the vector space will have three components, then its basis should have three components. So this be a vector space having three components, and this be a set of vectors having three components. Now this set capital S is a subset, or maybe subset or may not be subset of V. Will said or will be said of basis of V if it holds two conditions. If it holds two conditions. Number one, all the elements of the set S are linearly independent. All the elements of the set capital S are linearly independent. Linearly independent of what? Linearly independent of the elements of capital S. This is first condition and most important condition. Second condition is, by the help of the elements of capital S, we can generate the vector space capital V. By the help of the elements of capital S, we can generate V. Means each and every element of capital V can be expressed as some linear combination of the elements of capital S. Okay, that is capital V equals to linear span of capital S. So if capital S holds these two conditions, first condition is what? First condition is all the elements of capital S should be linearly independent, and second condition is capital S can generate capital V. That is, all the elements of capital V can be expressed as some linear combination of the elements of capital S. Then we can say that capital S is a basis of capital V. Now we have to remember few points. Number one is, basis is not unique. Basis is not unique. Means a vector space may have many bases. Okay, for a three-dimensional vector space, for a three-dimensional vector space 1 0 0 comma 0 1 0 comma 0 0 1 is known as a standard basis. For a two-dimensional vector space 1 0 comma 0 1 is called a standard basis, and so on. And in my next example, or in my few next examples, I will show you how we can find basis from the standard basis of a given vector space. So come to the definition of basis. Let capital V be a vector space over a field capital F. A set capital S of vectors in V. A set capital S of vectors in V is said to be a basis of V if S is linearly independent. You know how we can show the elements of a set are linearly independent or linearly independent. So first we have to verify S is linearly independent in V, and then S generates V, that is V equals to linear span of capital S. Next point, the number of elements in a basis of the vector space V. The number of elements in a basis of the vector space V is called the dimension or rank of V. Okay, so come to our main topic, that is dimension. What is dimension? Basis is what? Basis is nothing but a set, and we know this is a non-empty set. This set has certain rules. Now the number of elements of this set is called dimension of the vector space capital V. Alright, suppose the basis has 3 elements, then we say that the dimension of the vector space is 3. So the number of elements in a basis of the vector space V is called the dimension or rank of V. That is, the dimension of V equals to number of elements of the basis of V. Alright, now let us consider an example. Show that the vectors 1 2 1, 2 1 0, 1 minus 1 2 form a basis of the vector space V3 over the field of real numbers. Means this is not a problem to find dimension. Here we have to show that these elements will form a basis of this vector space. Okay, actually this V3, this 3 represents the dimension of this vector space. Okay, V3 means 3 represents the dimension of the vector space. So let capital S equals to second bracket open 1 to 1, this is our first element, 2 1 0 second element, 1 minus 1 2, this is our third element. First element, second element, third element. Now you see V3, and here each element of S has the 3 components. This is our first component, second component, third component, and so on. Okay. So S will be a basis of V3 if all the elements of S are linearly independent and S generates V3. So let us verify whether the elements of capital S are linearly independent or what. So to do so, we have to consider 3 arbitrary scalars C1, C2, C3, so that C1 into first element plus C2 into second element plus C3 into third element equals to 0 0 0. This implies C1, 2C1, C1 plus 2C2, C2, 0 into C2 is 0 only, plus C3, minus C3, 2C3 equals to 0 0 0, implies C1 plus 2C2 plus C3, 2C1 plus C2 minus C3, C1 plus 0 plus 2C3 equals to 0 0 0. Now comparing, we will get C1 plus 2C2 plus C3 equals to 0. 2c1 plus c2 minus c3 equals to 0, c1 plus 2c3 equals to 0. Now we have to find the values of c1, c2, c3. To find the values of c1, c2, c3, you may apply Cramer's rule, you may apply elementary row operations, you can apply matrix inversion method. Here I have applied cross multiplication method by considering the first two equations. Okay, that is, solving the first two equations, we get c1, this 2 into minus 1 minus 1 into 1 equals to c2 is this 1 into 2 minus 1 into minus 1, okay, equals to c3 is 1 into 1 minus 2 into 2. Okay, so the result is c1 by minus 3 equals to c2 by 3 equals to c3 by minus 3. So just divide all the denominators by minus 3, will get c1 by 1 equals to c2 by minus 1 equals to c3 by 1, and take as lambda. What is lambda? Lambda is any real number. So c1 will be 1 into lambda, that is lambda, c2 is minus lambda, c3 is lambda, right? Now we have to consider these values of c1, c2, c3 in our third equation. So the result is lambda plus 2 into lambda equals to 0, that is 3 lambda 0 implies lambda equals to 0. So if lambda equals to 0, then c1 will be 0, c2 will be 0, c3 will be 0. So we can say c1 into 1 to 1 plus c2 into 2 1 0 plus c3 into 1 minus 1 2 equals to 0 0 0 implies c1 equals to 0, c2 equals to 0, c3 equals to 0. So this is the condition that the elements 1 to 1, 2 1 0, 1 minus 1 2 are linearly independent. So our first condition is achieved. Now we have to deal with the second condition. But we already know that the dimension of the vector space is 3. Alright, now there is a theorem related to dimension. The theorem states that if capital V be a vector space of dimension n over a field F, then any subset of n vectors of V whose elements are linearly independent will be a basis of V. Alright, means if the dimension equals to number of elements of a subset of V and the elements of that subset are linearly independent, then that subset will be a basis of V. Now see, here the dimension of V3 is 3. Here S has 3 elements, first element, second element, third element, and the elements are linearly independent. So according to this theorem, we can say that capital S is a basis of V3. Okay. Now, if this type of problem will come in your exam, then you must mention this theorem. Now come to our next example, example number 5. If capital V be a vector space with alpha, beta, gamma as a basis, then prove that the set alpha plus beta plus gamma, comma beta plus gamma, gamma is also a basis of V. Means this is given that this is a basis and we have to verify this set is also a basis of V. So we consider this set as S1 and this second set as S2. Since S1 is a basis of V, therefore the dimension of V is 3 because S1 has 3 elements. Also, these elements alpha, beta, gamma are linearly independent. Alright, that is, we can say for any arbitrary elements A, B, C, A alpha plus B beta plus C gamma equals to 0 implies A equals to 0, B equals to 0, C equals to 0. Okay. Now we have to show that this set is also a basis of the vector space V. Now say S1 has 3 elements, S2 has 3 elements. These elements are linearly independent. Okay. So dimension of V is 3. Here the number of elements of S2 is also 3. So according to our previous theorem, if these elements are linearly independent, then S2 will also be a basis of capital V. So let us verify whether these elements are linearly independent or not. To do so, let us consider any three arbitrary elements C1, C2, C3 such that C1 into alpha plus beta plus gamma plus C2 into beta plus gamma plus C3 into gamma equals to 0, which implies C1 into alpha plus C1 into beta into C1 into gamma plus C2 into beta plus C2 into gamma plus C3 into gamma equals to 0. Now we have to consider like this: C1 alpha plus C1 beta, and here C2 beta. Beta common, then C1 gamma, C2 gamma, C3 gamma, gamma common. Now if we consider or comparing on both sides, C1 into alpha, C1 will be 0, C1 plus C2 will be 0, and C1 plus C2 plus C3 will be 0, because alpha, beta, gamma are linearly independent, and we know if alpha, beta, gamma are linearly independent, then their coefficients means C1, C1 plus C2, and C1 plus C2 plus C3 will individually are linear, are 0, right? So C1 equals to 0, and C1 plus C2 equals to 0, and C1 plus C2 plus C3 equals to 0, which implies C1 equals to 0, C2 equals to 0, and C3 equals to 0. So if we come to this line, C1 into alpha plus beta plus gamma plus C2 into alpha, beta plus gamma plus C3 into gamma equals to 0 implies C1 equals to 0, C2 equals to 0, C3 equals to 0. That is, by the definition we can say these elements are linearly independent. Also the dimension of V is 3 and S2 has 3 elements, so we say that S2 is also a basis of V. Okay, so this way we can show basis. Now come to example number 6. In this example, we will consider another very important theorem. Here I will not discuss details on the theorem, I just consider the statement of the theorem. Okay, this theorem is known as replacement theorem. Now just read the question first. Find a basis containing the vectors 1, 2, 0 and 1, 3, 1 for the three-dimensional Euclidean space R3. So here R3 is our vector space. Okay, we have to find a basis. Okay, we have to find a basis which contains these two elements. So this is our question. I said earlier that, okay, let us read replacement theorem. If alpha 1, comma alpha 2, comma dot 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 alpha n be a basis of a vector space V over a field capital F and a non-zero vector beta of V is expressed as beta equals to C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 plus dot 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 plus Cn alpha n, where C be any scalar of the field capital F. Then if Cj not equals to 0, then alpha 1, alpha 2, dot 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 alpha j minus 1, beta alpha j plus 1, comma dot 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 alpha n will be a new basis of V. That is, beta can replace alpha j in the basis. Means, suppose this is our basis, okay, and capital V be a vector space. As this is our basis, so any element of capital V, let beta, can be expressed as some linear combination of these elements like this way. Now beta can be replaced by any one of them, means beta can replace alpha 1 or alpha 2 or alpha 3 provided the coefficient should be not equals to 0. If C1 is not equals to 0, then beta will replace alpha 1 to form a new basis. If alpha 2, if the coefficient of alpha 2, that is C2, is not equals to 0, then beta can replace alpha 2 to form a new basis like this. Okay, so come to the solution. We know that for V3 or three-dimensional vector space 1, 0, 0, 0, 1, 0, 0, 0, 1 is a standard basis of R3. Now our first element is 1, 2, 0. So let us express 1, 2, 0 by the help of these three elements like this way. Okay, you see here this element is 0, so this cannot be replaced. So either this can replace or this can replace. So let us replace this element 1, 0, 0 by 1, 2, 0 by replacement theorem. So the new basis will be 1, 2, 0, comma 0, 1, 0, comma 0, 0, 1. All right, because this is not equals to 0, you can also replace this one, any one of them. Okay, right? So this is our new basis. Now we have to express this element by the help of these three elements, and this is our technique. 1, 3, 1 equals to 1, 1 to 0 plus 1 0 1 0 plus this is 1 0 0 1. Okay, you have to do it by yourself. Now you see here, this is not a non-zero term, this is non-zero term, this is non-zero term. So we can replace this term, this element, or this element, or this element. But if we replace this element, then our new basis will not have this element, right? Because we have to form a basis which will have this element and this element. So we have to keep this element in our basis. So either we have to replace this or we have to replace this, because in both cases the coefficients are non-zero. So let us replace this element by this element by replacement theorem. So our new basis will be 1 2 0, this is fixed, then replaced this by this 1 3 1 comma 0 0 1. Okay, so this is our new basis, and this is the application of replacement theorem. Now next question, and this is our very much topic related question. Here we have to find dimension of a subspace. Okay, dimension of a subspace. Now read the question. Find the dimension of W equals to second bracket open, first bracket xyz, first bracket close, belongs to R3, so that x minus 4y plus 3z equals to 0. So this is our criteria of this set. We have to find the dimension of this set. So given W equals to xyz belongs to R3 such that x minus 4y plus 3z equals to 0. Okay. Let alpha be any arbitrary element of W. If alpha be any arbitrary element of W, and let alpha equals to x1, y1, z1. Since alpha belongs to W, then we can say alpha should satisfy the condition of W. Here the condition is x minus 4y plus 3z equals to 0. So we can write x1 minus 4y1 plus 3z1 equals to 0, or x1 equals to 4y1 plus 3z1. This is quite interesting. Okay. Now x1 comma y1 comma z1 equals to x1 is replaced by 4y1 plus 3z1 comma y1 comma z1. So this can be written as 4y1 comma y1 comma 0 plus 3z1 comma 0 comma z1. You can verify this by adding this, you will get this element, the before one. Okay. Now taking y1 common from the first and z1 common from the second, you will get y1 410 plus z1 301. Now see, this element can be expressed as some linear combination of 410 and 301, right? We can say this element x1 y1 z1 can be expressed as some linear combination of 410 and 301. Okay. Also, this element is nothing but an arbitrary element. So in other words, we can say 410 301 can generate all the elements of W. That is, W can be generated by these two elements. So W will be a linear span of these two elements. W will be a linear span of these two elements. Okay, that is W equals to linear span of second bracket open 410 301. So this is our W. Now we have to verify whether these two elements are linearly dependent or independent. We know two elements, say alpha and beta. If these two elements are linearly dependent, then there must have a non-zero scalar lambda such that alpha equals to lambda into beta. Alpha equals to lambda into beta. Alpha equals to lambda into beta. Okay? And if alpha and beta are linearly independent, then this lambda will be 0. Alright? Now to verify so, we consider two scalars C1 and C2 such that C1 into 410 plus C2 into 301 equals to 000. Then doing simplification, we see we have C1 equals to C2 equals to 0. So this is the condition of linearly independency. That is, in other words, we can say 410 301 are linearly independent. So 410 301 is a basis of W. Now we know that this set is a basis of W. Now tell me, what is the number of elements of this set? The number of elements of this set is 2, right? Because this set has exactly 2 elements. Therefore, dimension of W is 2. Okay? Quite interesting. Now come to our next question. Show that W equals to, second bracket open, xyz belongs to R3 such that 2x minus 3y plus 5z equals to 0, comma, x plus 4y minus z equals to 0 is a subspace of R3. Find the dimension of R3. This is very important question. First we have to show that W is a subspace, then we have to find the dimension of this subspace. Okay, so we know how can we find subspace, because I have already show you in my previous video how we can show a set is a subspace of a vector space. To do so, we consider any two arbitrary elements alpha beta from this set such that alpha plus beta also belong to this set, and for any arbitrary constant c into alpha also belong to the set. C into alpha also belong to the set. If these two condition holds, then we can say that the set W is a subspace. If you not remember this, you should watch my video once more, okay? Then come to this video. Though, first we have to show that this set W is non-empty. How? See, 0 is a real number. Also 0, 0, 0 belongs to R3, right? Now, we show that 2 into 0 minus 3 into 0 plus 5 into 0 equals to 0, and 0 plus 4 into 0 minus 0 equals to 0 means 0, 0, 0 satisfies both the conditions of W. So we can say 0 belongs to W, because to be an element of W, the element should satisfy the condition of W and vice versa. So 0, 0, 0 holds the condition of W and 0, 0, 0 belongs to W. So W is non-empty. Next, come to second condition. That is alpha plus beta belongs to W. How? Let alpha comma beta be any two arbitrary elements of W. Then alpha belongs to W and beta belongs to W. Here we consider alpha equals to x1 comma y1 comma z1 and beta equals to x2 comma y2 comma z2. So definitely these both elements will satisfy these conditions. That is 2x1 minus 3y1 plus 5z1 equals to 0, x1 plus 4y1 minus z1 equals to 0, and 2x2 minus 3y2 plus 5z2 equals to 0, and x2 plus 4y2 minus z2 equals to 0. Let us mark this equation as equation number A. Now what is alpha plus beta? Alpha plus beta is x1 y1 z1 plus x2 y2 z2. That is x1 plus x2 comma y1 plus y2 comma z1 plus z2. Now to verify whether alpha plus beta belongs to the set capital W, we first verify whether alpha plus beta satisfies the condition of W. So let us verify. The conditions of W are this and this, okay? That is 2x minus 3y plus 5z equals to 0 and x plus 4y minus z equals to 0. So let us put the values here. X is x1 plus x2, y is y1 plus y2, z is z1 plus z2. So just putting the values in the first condition, we see that this is 0, because this is 0 by equation number A and this is 0 by equation number A, okay? And the second condition is what? X plus 4y minus z equals to 0. So x is x1 plus x2, y is y1 plus y2, z is z1 plus z2. By simplifying we get 0, because x1 plus 4y1 minus z1 is 0 according to this, and x2 plus 4y2 minus z2 is 0 according to A. So both the conditions are satisfied by alpha plus beta. So we can say alpha plus beta belongs to W. That is our first condition holds. Now come to our second condition, that is C alpha belongs to W. So we consider any arbitrary element C belongs to R. So that C alpha will be Cx1, Cy1, Cz1. Now come to first condition, that is 2x minus 3y plus 5z. This is our x, this is our y, this is our z. Simplifying we get 0. And x plus 4y minus z, that is C common, this is also 0. Means both the conditions are satisfied by C alpha. So we can say that C alpha also belongs to W. So see, W is non-empty, very important. First we have to verify whether W is empty or non-empty. Yes, it is non-empty. then alpha plus beta belongs to W, hold, then C alpha belongs to W, hold. So we say that W is a subspace of R3. Okay, now we have to find dimension of this subspace. We have to find dimension of this subspace. How? Since alpha equals to x1, y1, z1 is an arbitrary element of W. This arbitrary means alpha is x1, y1, z1 is an arbitrary element of W. So definitely alpha satisfies the conditions of the set W. That is 2x minus 3y plus 5z equals to 0 and x plus 4y minus z equals to 0. That is 2x1 minus 3y1 plus 5z1 equals to 0 and x1 plus 4y1 minus z1 equals to 0. Now we have to solve these equations by cross multiplication method. x1 y1 z1 minus 3 into minus 1 minus 4 into 5 equals to y1 by 2 into minus 1 minus 5 into 5 into 1. First is 5 into 1 minus 2 into minus 1. Okay. Then for z, 2 into 4 minus 1 into minus 3. Alright. That is x1 by minus 17, y1 by 7, z1 by 11, and let this is as lambda. So x1 will be minus 17 lambda, y1 will be 7 lambda, and z1 will be 11 lambda. Right. So we can write x1, y1, z1 equals to minus 17 lambda, comma 7 lambda, comma 11 lambda. Lambda taken as common, minus 17, comma 7, comma 11, where lambda is any real number. Now see, this x1, y1, z1 can be expressed as some linear combination of minus 17, 7, 11. Again, come to our concept. This is arbitrary. So any element can be expressed as a linear combination of minus 17, 7, 11. That is, all the elements of W can be expressed as some linear combination of minus 17, 7, 11. That is, W is a linear span of minus 17, 7. Okay, W is a linear span of minus 17, 7, 11. Okay. Now, this set has exactly one element, minus 17, 7, 11. So definitely, as this is a single element, and therefore it is linearly independent, because single element are always linearly independent. So we can write minus 17, 7, 11 is a basis of W, right? So this set is a basis of W. Now tell me, what is the number of elements of this set? Definitely the number of elements of this set is 1. So by definition, dimension of W is 1. Hence dimension of W is 1.